The most capable surface warship in the world cannot reload its missiles at sea, and it was no accident. The Navy made this choice deliberately, held it for nearly 40 years and never went back. Then the Red Sea happened, and the Navy rediscovered a problem it had already solved once and then deliberately removed. The ships had to leave, not because they lost, because the cells were empty and there was no mechanism to fill them. And the Navy started looking at a ship it had spent years trying to figure out what to do with. 785 feet, 83,000 tons kept alive by a skeleton crew of 33 civilian sailors. No mission pending decommissioning, tied to a pier in San Diego, Montford Point. A hull built on the design of a commercial crude oil tanker, converted into a floating pier that can sink itself halfway into the ocean and rise back up. The Pentagon had recommended scrapping her. Congress blocked it, but no one could explain exactly why she was worth saving. This is Navy Decoded, and we're going to show you exactly why. To understand why a 1980s engineering bet just blew up in the Navy's face, we have to start with the weapon that defined the modern surface fleet. In September 1986, the United States Navy commissioned USS Bunker Hill, hull number CG-52, a Ticonderoga-class cruiser. Bunker Hill was the first warship to carry a new launch system called the Mark 41 vertical launch system. The Mark 41 ended a problem. Old missile launchers fired one round, rotated, reloaded, fired again. Slow, mechanical, sequential. The Mark 41 broke that constraint entirely. 8 cells per module up to 96 cells on a Flight I Arleigh Burke, 32 forward of the bridge, 64 aft. Any cell, any moment, any missile, vertical, independent, instant. But every weapons engineer knows a magazine eventually runs dry. So the original Mark 41 design included a strike-down module, a 5-cell unit with a collapsible crane folded into the launcher itself. The crane could lift a 3,000 canister from a supply ship pulled alongside, swing it across, and lower it into an empty cell. It worked at the pier, it worked in flat water, it did not work when the sea moved. By the late 1990s, the Navy made a choice. The strike-down crane was complex. It occupied 5 cells that could otherwise hold missiles, and it only functioned reliably in sea state 3 or lower, which is almost never the case in open ocean. So they pulled it. Every Arleigh Burke launched from that point forward shipped without a reload mechanism. The bet underneath that decision was simple. The United States Navy fights from positions where it can return to port. It controls the Atlantic, the Mediterranean, the Western Pacific. There are always Allied bases within reach. There is no plausible scenario where a destroyer fires every missile in its magazine before resupply. That bet held for nearly 30 years until the Red Sea came to collect. Everything a Flight I Arleigh Burke can do beyond visual range fits inside 96 holes in the deck. And the moment she leaves port, that number is fixed. It cannot be replenished at sea or expanded under fire. Air defense, anti-ship, land attack, ballistic missile intercept, 96, and then the geometry of the fight changes. And 96 is not an arbitrary number. Every cell sits high in the hull, each holding a missile that can weigh as much as a small car. Stack more of them, and the center of gravity climbs. You trade away stability, speed, and seakeeping for magazine depth. 96 is roughly where the naval architecture stops paying off. Once they are empty, the ship still has its deck gun, its phalanx, its torpedoes. But the rest of it, the layer that defines what an Aegis destroyer is gone. No single destroyer exhausted its magazine in the Red Sea. That is not the point. The point is the rate, and what the rate tells us about a real fight. Over 15 months of running engagements against Houthi drones and cruise missiles, U.S. destroyers fired more than 220 interceptor missiles. 120 Standard Missile 2s, 80 SM-6s, around 20 ESSMs and SM-3s, total cost approaching $2 billion. Many of those interceptors cost between $4 million and $28 million per shot, fired at simple attack drones costing as little as $5 to $10,000 apiece. The Houthis are not a peer adversary. They do not field a fleet, they do not field an air force in any meaningful sense. They're launching what they can find or build, mostly Iranian-supplied components assembled into one-way attack drones. And they still made the math fail. USS Carney returned from a single deployment with 51 separate engagements logged. In one 10-hour battle, she took down 15 drones and 4 cruise missiles. This is what running low looks like. And these ships did not face a pier. Think of it as a fire truck built to carry exactly 1 load of water. Enough for 1 house fire, no way to refill in the field. For most fires in the last 40 years, that was enough. What we are planning for now is not a house fire. Now apply that math to the scenario we actually have to plan for. China fields the densest anti-ship missile arsenal on the planet. The DF-21 Delta anti-ship ballistic missile reaches roughly 800 nautical miles. The DF-26 reaches is 2,200 nautical miles. Subsonic cruise missiles, supersonic cruise missiles, hypersonic glide vehicles, drone swarms, all of it engineered specifically against U.S. carriers and destroyers. In that environment, a destroyer burns through 96 cells in hours, not months. And when the magazines run dry, the ship has to leave the fight. From the Taiwan Strait, the nearest reload port is Yokosuka, 3 to 4 days at cruising speed. Pearl Harbor is 7 to 8 days. San Diego is well over 2 weeks. Every day a destroyer is in transit, that hull is not in the fight. This is the single magazine curse, one full load of missiles, no way to refill at sea. The Navy has lived with it for nearly 40 years, because until recently no one fought hard enough or long enough to find the floor of the magazine. The Red Sea found the floor, the Pacific would find it faster. So the engineering question becomes simple to ask and hard to answer. How do we reload a destroyer that cannot afford to leave the fight? The Navy did not forget the problem. They just deferred the solution. In the 1990s, an engineer at the Naval Surface Warfare Center in Port Hueneme, California, a man named Marvin Miller, began designing what we now call TRAM, the Transferable Reload at Sea method. What we were attempting was mechanically straightforward to state. Mount a hydraulic transfer system on a supply ship, pick up a missile canister, swing it across the gap between two ships, and lower it vertically into an empty VLS cell on a warship steaming alongside. Simple to describe, difficult to engineer, here is the physics. Two ships steaming side by side are not still. The supply ship moves, the warship moves. Each one rolls, pitches, yaw, surges, sways, and heaves, 6 degrees of freedom. Even in a moderate sea, the relative motion between two hulls can shift the position of a target cell by several feet over the course of a few seconds. A Vels measures roughly 25 in squared. The canister has to drop into that cell vertically within an inch or two of tolerance, while the cell itself is moving in 3 dimensions. That is the engineering equivalent of threading a needle on a moving train from another moving train. The 1990s prototype work showed it was possible. The funding never showed up. The Cold War was over. The Navy had budget cuts to absorb. There was no opponent forcing the question. The Red Sea became that opponent. In July of 2024, the Navy ran a land-based TRAM demonstration at Port Hueneme. 3 months later, they took the system to sea. On the 11th of October, USS Chosin, a Ticonderoga-class cruiser hull number CG-65, pulled alongside USN's Washington Chambers, a Lewis and Clark-class dry cargo ship in the Pacific Ocean off San Diego. Sea state 4, waves running up to 6 feet. The two ships ran parallel courses at the standard alongside replenishment distance. The hydraulic transfer arm extended out from Washington Chambers. It carried a single test canister, instrumented but identical in weight and form factor to a live missile. The arm moved, the canister cleared the gap, rotated and lowered. It seated into a Vels on Chosin. For the first time in the history of the Mark 41 vertical launch system, a U.S. Navy warship was reloaded at sea. Secretary of the Navy Carlos Del Toro called it game-changing. The Navy released music footage. The defense press did not stop talking about it for a month. But one successful test is not a fleet capability. TRAM is only the mechanism. It moves the canister between ships and nothing more. Scale requires more than a transfer arm. You need a supply ship large enough to carry hundreds of canisters, a deck stable enough that cables do not snap when the sea rises, and a forward presence the fleet can sustain, not a one-off. The Navy is exploring 3 solutions in parallel. TRAM on existing logistics ships proven by the October test, crane ships underway demonstrated by USN's Gopher State during large-scale Exercise 25, and a commercial speed reloader from Lidos targeting 6 to 8 cells per cycle. All 3 move canisters from one ship to another, but none of them is a platform. To make the system real at scale, the fleet needs a ship large enough, stable enough, and dedicated enough to be the floating armory. And the Navy, almost by accident, already owned exactly that ship. The answer was sitting at a pier in San Diego waiting to be scrapped. USN's Montford Point was built for tanks. General Dynamics NASSCO laid the keel in 2011, delivered to Military Sealift Command in May of 2013. Hull classification at delivery, TMLP-1 Mobile Landing Platform. In September of 2015, the Secretary of the Navy reclassified the type as TESD Expeditionary Sea Base, and Montford Point became TESD-1. The design is based on a commercial Alaska-class crude oil tanker hull, 785 feet long, 83,000 tons at full load. Dozens of ballast tanks that flood and pump in sequence, sinking the deck low enough that landing craft can drive directly onto it from the water, then rising back up to carry them across the ocean. Montford Point was built for one job: take 58 Abrams tanks off a logistics ship parked skin to skin alongside her and deliver them to a beach somewhere in the world, a floating pier for amphibious operations at scale. By 2022, that mission had quietly disappeared. The Marine Corps' Force Design 2030 doctrine moved away from large amphibious assaults. Smaller, distributed missile-armed Marine units replaced the divisional landing concept. Montford Point's job stopped existing. The Pentagon's fiscal year 2023 budget proposed retiring her. Congress blocked the decommissioning and ordered the ship moved into reduced operating status. 33 civilian mariners stayed aboard. The deck went quiet. The ship sat at the pier. In early 2025, the Navy stripped the legacy core capability set, the equipment installed for amphibious work, off the mission deck. The platform went back to bare steel. Then the fiscal year 2027 budget request landed. Inside, it was a line for $177.7 million titled Shipboard Crane Systems and Shipboard Cargo Systems. Tucked into that umbrella line was funding for the ASRF program at sea reload of VLCs and the demonstration platform USN's Montford Point. The same characteristics that made Montford Point too specialized for the Marine Corps made her exactly right for the Navy's new problem. 25,000 square feet of open deck, enough to hold hundreds of missile canisters in a magazine layout. Ballast tanks running the full length of the hull. A crude oil tanker hull strong enough that the weight of canisters and a heavy crane is not a concern. Montford Point can take canisters from commercial cargo ships pulled skin to skin alongside, the same way she once took tanks. And she is already in the fleet inventory, no new construction required. And this is the part that matters most. Remember the transfer problem? 2 hulls moving in 6 degrees of freedom, the target cell shifting feet in seconds. Mass is what fights that. 83,000 tons ballasted load does not roll the way a lighter hull does. The more stable the receiving platform, the smaller the relative motion tram has to chase. So a reload that fails against a standard logistics ship in Sea State 4 becomes possible against Montford Point and worse. Her stability is not a convenience. It is the physics that makes the system work. From there, the concept of operations is almost obvious. We anchor Montford Point beyond the DF-21 Delta envelope, roughly 800 nautical miles from the fight. That puts her somewhere near Guam, potentially within range of the DF-26 at 2,200 nautical miles, which means Montford Point is not safe. She is safer, and in the Western Pacific, safer is the best available option. She holds hundreds of canisters, resupplied continuously by commercial cargo ships from the United States. When an Arleigh Burke runs dry, she sails 1 to 2 days back to the armory, reloads, and returns to the fight. A destroyer that would otherwise spend 7 to 8 days round trip to Yokosuka spends 2 to 3 days to Montford Point, assuming she is positioned correctly and assuming the escort math pencils out. But the engineering cannot close the whole gap on its own. Montford Point becomes the apex node. Every destroyer in the Western Pacific routes back to her for reload. Every commercial cargo ship out of the United States routes to her with fresh canisters. She is the single most valuable target on the ocean, and she carries no defenses. No Aegis radar, no interceptor missiles, no slow-moving box packed with hundreds of missile canisters. And her self-defense kit is zero. To keep her alive, the Navy has to pull destroyers off the front line to escort her. The destroyers exist to fight forward. The floating armory exists to keep them fighting forward. So now the floating armory needs the destroyers to protect it, pulling destroyers off the very mission the armory was built to enable. You dilute frontline combat power to protect your logistics chain. You protect what protects you. The escort problem is tactical. The production problem is structural. Together, they define the ceiling of what Montford Point can actually deliver. There is a second problem underneath. The United States produces SM-6 interceptors at roughly 150 per year. The Navy is racing to more than triple that production rate by 2028. But a single week of high-intensity Pacific combat could burn through years of stockpile. Montford Point is not a missile factory. She is a missile pipeline, and no pipeline matters if the reservoir behind it is shallow. This is what Navy Decoded is for, not the announcement, not the footage release. What happens when you follow the engineering past the press conference? The Navy almost scrapped Montford Point. 40 years of assuming the fleet would never fight long enough to empty a magazine. Then one 15-month campaign against a group with no air force, no fleet, and a budget smaller than the cost of a single destroyer's missile load proved the assumption wrong. The answer to a problem nobody wanted to admit came from a hull sitting idle on a pier in San Diego waiting to be cut apart for scrap. TRAM can move missiles between ships. Montford Point can hold them at the edge of the battlefield. The single magazine curse has a working answer built from the ship the fleet almost threw away. The Navy is building the world's best gas station, but a gas station is only as good as the supply chain behind it. The United States produces 150 SM-6 interceptors per year. A peer fight in the Western Pacific could burn through years of that stockpile in a single week. The ship is ready. The mechanism works. Can the United States build missiles fast enough to fill her before it matters?